Okay, I'm going to continue looking at some related rates examples. This time a classic, yet a little silly example involving a ladder that's leaning against a house. It's 13 feet long, and here's the diagram showing the ladder. So again, the important thing to realize here is the length of this ladder is not variable. The length of this ladder is fixed. It's not a collapsible ladder or anything. It's going to be maintaining that length 13 feet. So that's not a variable, so I'm not going to assign a variable to the length of the ladder. It's 13 feet. But the bottom of the ladder is being pulled away from the house at a constant rate of 2 feet per second, as this arrow shows. The bottom of this ladder is rolling away. And at the same time, though, the top of the ladder maintains contact with the house, and it's going to therefore slide down. If you think about it, if this ladder base here, bottom is pulled away this way, then the top of the ladder is going to come down. And so this question involves some rates of change in here. It's kind of a silly ladder. We're going to neglect any friction or anything, and so it's kind of like there's a wheel or ball bearing up here at the top and bottom. Not a very stable ladder, not one you'd want to get on in the real life. The quantities of interest, though, what's changing in here? Well, in this problem, we're told that the bottom of the ladder is pulled away from the house at a constant rate. And so if I think about the distance from the house to the bottom of the ladder, that distance is changing, right? Obviously, over time, that distance is getting bigger, is it not, right? As the bottom of the ladder moves away, that distance is getting bigger. But it's a variable quantity, so we need to assign a variable to it. I'm going to call that x. We kind of think of that as the horizontal direction there. We'll call that x. The other quantity that's changing is what? The height of the ladder. In fact, notice question A says, how fast is the top of the ladder moving down the side of the house? So the top of the ladder, we're interested in how high it is above the ground. So that's variable as well. As we said, that's changing. I'm going to call that y. And so in the problem, again, what rate is given and what rate are we asked to find? Well, in this particular one, we're, of course, given that the ladder is pulling away at a rate of 2 feet per second. So what rate of change are we talking about? What derivative are we talking about? The answer is dx dt. dx dt. That's the rate of change of x with respect to time. And that rate of change is equal to what? 2 feet per second. And notice it's positive because x is going to get larger, right? X is increasing as time progresses. What rate of change are we asked to find? How fast is the top of the ladder moving down the side of the house? Well, that's the rate of change of y with respect to time. And we're asked to find that the instant when what? When it is 12 feet above the ground, when the ladder is 12 feet above the ground. What do we mean about that? Well, we mean the value of y, right? That's the height, when y is 12. So remember, y is not constant. You don't want to plug in y equals 12 until you've found the related rates equation. Okay. So what is the equation we're going to use to find the related rates equation? What is the equation that relates these variables of interest? Well, I hope that you see we have a right angle here, assuming the house is 90 degrees with the ground. We'll assume level ground here, so no slopes or anything. And so, yeah, we have a right triangle here, and we know the side of the hypotenuse of this right triangle is 13. That's not changing. But these two side lengths are x and y. They are changing. What's the equation from Pythagorean Theorem? Okay. Now 13 squared, of course, is 169. Keep in mind, that is a constant quantity. It's not changing. X and y are changing, though. So this comes from Pythagorean Theorem. So what do we do next? We take the derivative with respect to time. So I'm going to take the derivative with respect to time of both sides of this. Now notice we are using implicit differentiation when we do this. There is an alternative in the sense that we're finding dy dt. Somebody might say, could I solve for y and then take the derivative? The answer is yes, but you have to be careful. It gets a little cumbersome here because when I subtract x squared, in order to solve for y, I'm going to have to take the square root. And it gets a little messy when you throw in that square root. So I think the derivative taking process is going to be much more difficult. And so it is better a lot of times to just implicitly differentiate. So that's what we're doing with respect to time. So of course on this right hand side, what are we going to get? What do we get when we take the derivative with respect to time of this quantity? That's a constant. So I hope you all realize and say that that's got to be 0. The length of the ladder is not changing. Its rate of change is 0. Now over here, what do we have? The derivative with respect to time, right, of x squared plus y squared. I take the derivative with respect to time of each one of these. But remember, x and y are both variable quantities, right? They're changing with respect to time. And so what rule do I have to use? Again, it's the chain rule. X squared, the outer function is x squared. The derivative is 2x times the derivative of the inner function x. That's dx dt. Plus, same thing here. Derivative of y squared by the chain rule is 2y times the derivative of the inner function, dy dt. And now we could, at this point, plug in values we know. But I'm going to go ahead and solve for dy dt. I'm going to solve for dy dt in this equation and then plug in. And the way I'm going to do that is I'm going to subtract this quantity, 2x dx dt, from both sides of the equation. So 0 minus that is negative 2x dx dt. And I'm going to divide by 2y. And of course, 2 divided into negative 2 is negative 1, x divided by y, so I get negative x divided by y dx dt. Now I can answer the question, right? dy dt, the instant that what? Y is 12, is what? Well, it's negative x over y. Now I know what y is. I can plug in 12 for y. And dx dt, do we know what that is? That's the given rate of change that we already have here. That's 2 feet per second. So we're given that. Well, the question is up here, what about x? What is x? Where do I know what x is anywhere in this process? Well, I don't yet, but I can find it. Because at the instant y is 12, what do we know? Well, when y is 12, this relationship holds, right? So when y is 12, x squared plus 12 squared is equal to 13 squared. And I can solve for x. So at the instant y is 12, I'll let you solve this. See if you get this. X turns out to be exactly 5 feet. When y is 12 feet, when y is 12 feet, x is 5 feet. Just at that instant. And so just at that instant, I can now plug in that value for x. This simplifies down, therefore, to negative 5/6. 2/12 is 1/6. And what are the units here? What are the units? What is dy dt's units? Negative 5/6 what? Y is the height in what? Feet. Time is in seconds again. Feet per second. Are you happy that we have a negative rate of change? Think about the value of y. Is it getting bigger or smaller? I think we're happy that it's negative, right? Okay, a little variation real quick on this one. The same picture is going to help us with part B. What is the rate of change of the angle between the ladder and the ground when the top of the ladder is 12 feet above ground? So now we're looking for the rate of change of the angle. Where's the angle between the ladder and the ground? Let's draw that. The angle between the ladder and the ground is right here. Is that constant or is that variable? Well, if you think about it as this ladder, the bottom is pulled away from the base of the house. The top is coming down the side of the house. do you see that that angle is indeed changing, and that over time it's getting smaller and smaller, and eventually that ladder will fall flat on the ground there and the angle will go to 0. But at any given time it's changed. So it's variable. I need to give it a variable. Let's call that theta. That angle is theta. So what do I need now? I need a relationship between theta and what? Y or x. What do we know? What are we given in this problem? Remember what we were given? Remember what we were given? dx dt? So what I want to do is I want to get theta in terms of x. Now if I've done this problem already, I also have dy dt now, so I mean technically I could get theta in terms of y, or I could even get theta in terms of x and y, but the best way to go about this is to get theta just in terms of x. So how do we do that? Well, this is a right triangle. What is theta? What is x in relation to theta? That's the adjacent side. Okay. So what trig function do I want to use? Do I want to use cosine or sine or tangent? Somebody might say tangent because tangent uses the opposite over the adjacent. That's y over x. The problem with that is you're bringing in y into the picture. Y is a variable. I would rather try and pull into the picture the hypotenuse, which is constant. Is there a trig function that relates the adjacent side of a right triangle to the hypotenuse? Yeah, sine. Sine of theta is x over the hypotenuse, which is 13. That's going to greatly simplify things. So again, down here, we're given the same rate. And this time we're asked to find d theta dt. Again, when what is 12 feet? Remember y. When the ladder is 12 feet above the ground. Same thing when y is 12. Okay. Of course, we know when y is 12 feet from above, we also know that x is 5 feet. Right? That instant. Of course, we're not going to plug these values in until we get the related rates equation. Okay. And so the equation I'm going to use, I messed up when I was saying sine. Excuse me, I was saying sine is adjacent over hypotenuse. That's not right. Sine is opposite over hypotenuse. I apologize. What I should be using is what? Adjacent over hypotenuse is the cosine function. So forgive me if you were very confused about that a minute ago. You are rightfully so confused. Cosine of theta is adjacent over hypotenuse. So that's what I'm going to actually use here. Cosine of theta is adjacent, which was x, over the hypotenuse, which was 13. Sorry about that. So sine of theta would be y over 13. Now again, you could do it that way if you've done this already. You know what dy dt is. If you haven't done this part, then you would not, I think, want to go that route. You would want to include y. And tangent I would avoid as well, even though it includes y and x. Tangent is opposite over adjacent, y over x. You could do it that way, but it makes the derivative process much more complicated. This is going to be much easier if you think about it. X divided by 13, when I take the derivative of that, you might be thinking, well, I've got to use a quotient rule. You really don't, because x divided by 13 is just 1/13 times x. 1/13 is a constant multiple. This is real easy to find the derivative of. When I take the derivative with respect to time of both sides, this right-hand side here is very easy. Right, the 1/13 is a constant multiple. It comes out. What's the derivative with respect to time of x? Well, that's simply dx dt. That's simply dx dt. What about over here? Well, we've got chain rule going on here. We've got derivative of time with respect to time of cosine of theta. So theta is a function of time. It's the inner function. The outer function is what? Cosine. So the derivative of the outer function cosine is what? Negative sine. Evaluate the inner theta times the derivative of the inner function, which is d theta dt. And now I can plug in the things that I know. Remember, we know that dx dt is given, right? That's 2 feet per second. So I can plug in 2 there And of course I'm asked to find d theta dt. Okay, so I'm going to find that. Question is right here, what is sine of theta? What is sine of theta going to be? Do I have to find theta in order to find sine of theta? The answer is no. Just go back to what we were talking about before. I incorrectly had said sine of theta is the adjacent side over the hypotenuse. That's wrong. Sine of theta is the opposite side of the hypotenuse. So sine of theta is y over 13. So, but at the instant y is 12, sine of theta is, again, y over 13. It's going to be 12 over 13. Right? Sine of theta is equal to 12/13. I don't even know what theta is right now. I could find it by using the inverse sine function or arcsine of 12/13. But I don't need it. There's no need to find theta because I know sine of theta is the opposite over the hypotenuse. And since I know the opposite side is 12 feet, I know that that ratio is 12/13. So that's going to tell me what to put in for negative what? Sine of theta, negative 12/13. And now if you look at this equation I have down here, I can now solve this for d theta dt. By doing what? By multiplying by what? The reciprocal of negative 12/13. What's the reciprocal of negative 12/13? Negative 13/12. Over here I get what? 2/13. Multiply that out, I get negative 1/6. Okay. Now, units. This is where it gets a little tricky. What are the units in this case? What are the units in this case? We're looking at the rate of change of theta, which is an angle with respect to time. Now, some people might say angle. That's degrees. So would it be degrees per unit time? Degrees per second? No, the answer is not that. If we go back to this problem, we look at the units involved. What are the units of sine of theta? Sine of theta. Well, sine of theta is the ratio of the opposite side to the hypotenuse. Those are lengths both, right? The top is feet, the bottom is feet. Feet divided by feet are unitless. Sine of theta is just a ratio. There's no units here. There's no units here at all. So this is unitless, no units, right? Where's this 13 come from? 13 comes from the length of the ladder, right? 13 is the length in feet, right? So the bottom down here we got feet. What's this 2 in? 2 is what? Feet per second. So what is feet per second divided by feet? Feet per second divided by feet. That's just per second. The units are literally per second. Does anyone know what the units are? The units are radians per second. Radians are a unitless measure of angle, and that's what unit we're getting out of this. If you wanted to convert this to degrees per second, you can. If you remember from trigonometry, in 180 degrees is equivalent to pi radians. So I can multiply by 180 degrees over pi radians to convert this to degrees per second if I wanted to. But I don't want to, and I don't expect you to have to do that either. Okay. We're going to take a look at one more example. One more example. So this was sort of two examples in one related to each other. And the one I want to take a look at now involves two cars. Okay. We have a blue car and a red car. So at noon, a blue car is 200 miles due east of a red car. Let's just draw that right now. What would it look like if the blue car was east of the red car? Well, east is to your right here. So if the red car is located here at noon, then the blue car, I'll draw it in blue, it'll be 200 miles due east. Let's say it's here, blue car. So this is 200 miles. So here's our blue car, right, at noon. And over here is our red car at noon. The blue car is heading due west at 40 miles per hour, and the red car is heading due south at 25 miles per hour. So let's think about this. After a short bit of time, during the first hour, or hour or two, or whatever it is, the blue car will have traveled a certain amount of distance, right? It's moving where? Due west. So it's heading right towards where the red car was at noon. So the blue car is moving here. So after some amount of time, the blue car is now at this location. So it's moved there. In the same amount of time, the red car is going to move as well, because the red car is heading due south. So its due south would be what? South would be going down, right? So it's moving down. Now it is going a little bit slower, right? 25 miles per hour versus 40. So it's not going to go quite as, the length here is not going to be as much as this. But here's the red car after that period of time. So the question is, how fast is the distance between the cars changing at 2 p.m. and then at 4 p.m.? And then we'll talk about the rest of things. So the distance between the two cars. Well, at this given time, right, what's the distance between the two cars? Well, it would be the length of this line segment connecting the two. Okay, I'm going to call that that distance. I'm not going to call it D. I'm going to call it L, just to avoid the infamous dd dt. If I take the derivative of d with respect to time, it comes out as dd dt. I just don't like that. So I'm going to use L for my distance between the two cars. And then what else is changing? Well, I've got a couple other variables. Now, the blue car is changing. I need a variable to represent the blue cars. And one thing you could talk about is let x be the distance the blue car has traveled. And you can do that, and that's fine. I'm going to do it a little different here, and I hope you'll understand why. I'm going to let the variable quantity be the distance from the blue car to where the red car was initially. So initially they're 200 miles per hour apart, and then as the blue car drives towards the red car, the distance from the blue car to the red car gets smaller. The distance from the blue car to the red car gets smaller. And I'm going to call that distance x. So notice x is going to be a variable. It's changing. It's getting smaller as time progresses. The other quantity I'm going to label is actually just the distance the red car has traveled. And I'm going to call that y. Notice y is getting larger. Right? Y gets bigger. I know you might be thinking, hey, we're going down. Isn't it negative? No. Y is just the distance. It's never negative. It's how far this thing has traveled. So as the red car moves further and further south, then y is just getting bigger and bigger and bigger and bigger. So that distance is increasing. But x, right, is clearly doing what? Getting smaller and smaller and smaller. Okay. Well, I think, do you see something here? I hope you see a triangle with a right angle here, right? Because if you're traveling due west and then you turn south, that's a 90-degree turn. So we have a right triangle. And so let's talk about information. What are we given? What rates are we given? Well, we're given two, actually. We're given dx dt and we're given dy dt. Let's talk about dx dt. What's dx dt? Well, that rate of change is going to be equal to the speed that the blue car is traveling, which of course is 40 miles per hour. But I want you to look at the picture, 40 miles per hour. Should this be negative or positive? Should this be negative or positive? Remember, this is the rate of change of x. X is this length. What's happening to this length, x? Is it getting smaller or is it getting bigger? It's getting smaller. So it's getting smaller, We need a negative sign there. The other rate of change we know is the rate of change of y with respect to time. And that's the speed of the red car. It's traveling at 25 miles per hour. Is it positive or negative? What's happening to y? Is y getting bigger or smaller? Again, over time, y is getting bigger. Y is increasing. So it's going to be positive. Right? Now, again, had you called x, for instance, the length that the blue car had driven, then that x would just be positive 40 miles per hour, because this blue length, the distance the blue car has traveled, that's getting bigger. So as x gets smaller, this length here between my fingers is getting bigger. So you could have done that. Now, the question is, what would this length be then that we're talking about here if this is x? Well, we've got the same sort of problem, because if x is this length, what would this length be? What would the distance the blue car traveled be? Well, if you think about it, the total distance from the blue car to where the red car was at noon is 200 miles. So if this length is x, then this length is going to be what? 200 minus x, whatever's left over. So if x is 70 miles, if there's 70 miles now from the blue car to the red car, that means the blue car must have traveled what? 200 minus 70, 130 miles. So when x is 70, this length would be 200 minus 70, or 130. What are we asked to find? How fast is the distance between the cars changing? Distance between the cars is L, so we're asked to find dl dt. And we're also asked to find it at different times. So what is our equation that relates our variables of interest, x, y, and L? What do you think? Right triangle? Looks like Pythagorean Theorem. So notice x squared plus y squared is L squared. There's my equation. I take the derivative with respect to time. Now keep in mind, unlike the ladder problem where we kind of had the hypotenuse was the length of the ladder, that was a fixed length. This L is changing. This distance between the car changes. It doesn't stay the same. And of course y and x are changing. So all of these x, y, and L are all changing with respect to time. So when I take the derivative of each piece here, I've got to use the chain rule. And they look similar. Derivative of x squared is 2x times dx dt. Derivative of y squared, 2y dy dt. And the derivative of L squared, 2L dl dt. Now notice real quick that I can divide both sides of this equation by 2. And I'm looking for dl dt. I can solve for dl dt by dividing both sides by L, or by multiplying by 1 over L, and that's what I'm going to do. dl dt is 1 over L times this stuff. And there's my related rates equation again. Now, in this particular problem, we are asked to find dl dt, the rate of change of the distance between the cars, right? The rate of change of the distance between the cars. At particular times, we're asked to find it at 2 p.m. rather, and 4 p.m. Remember, the initial setup was at noon. So what's happening at 2 o'clock? Well, at 2 o'clock, what is the value of x at 2 o'clock? Well, remember, the blue car travels at what? 40 miles per hour. So in 2 hours, how far has the blue car traveled? 2 times 40, 80 miles, right? This would be 80 miles. Well, what would x have to be? What's left? There was 200 miles initially. You've traveled 80 miles already. Right, so what's left? 120. So at 2 o'clock, the distance the blue car is to where the red car was at noon is 120 miles. So x is 120 miles at 2 o'clock. Similarly, what's y? Well, y, notice, is the distance the red car traveled. It travels 25 miles per hour. 25 times 2 is 50 miles. So at 2 o'clock, the distance y is equal to 50 miles. Okay. And notice, the other thing we're going to need, notice I've got dx dt and dy dt. Those were the given rates. I know what those are. Those are fixed rates, right? But, and I know x and y now. What about L? How do I find L? Well, notice the original equation that relates the variables of interest was the Pythagorean Theorem. So I know that x squared plus y squared is L squared at any time. So at this particular time, at 2 o'clock, I know x and y. I can now find L. L is what? The square root of x squared plus y squared. Just plugging in those values for x and y. And this comes out to be exactly 130. And so at 2 o'clock, dl dt, if I plug these values in, L is 130, x is 120. What was dx dt? Do you remember? Dx dt, negative 40. dy dt, positive 25. Plus y, which is 50, times dy dt, 25. Okay. So I'll have you evaluate that. When you do, you get approximately negative 27.3 miles per hour. At 4 o'clock, I'll have you check these values, but x is going to be 40 miles. And the reason being, right, 4 hours, the blue car traveling at 40 miles per hour will have traveled 4 times 40, 160 miles. That's how far the blue car has traveled, 160 miles. Notice x has gone down to 40. There's only 40 miles now from the blue car to where the red car was, because the total was 200. So x is equal to 40. And the red car is how far the red car is, the y is how far the red car has traveled. 25 miles an hour. It's 4 o'clock. It's 4 hours. That's 4 times 25, 100 miles. And then what's L? Right from above, it's going to be the square root of x squared plus y squared. Now, I'm going to let you, this doesn't come out nice number. If you can approximate this with your calculator, I'll let you do that. I'll let you, you do this. You check and see, plug in the values, and you see that the dl dt in this case is approximately equal to 8.36 miles per hour. So let's talk about these two. Notice at 2 o'clock, the rate of change of the distance between the cars is negative 27.3 miles per hour. What's that mean about the distance at that instant? Well, the negative quantity means the distance is getting smaller, right? dl dt being negative means this distance L is getting smaller at that instant. So the cars are getting closer together. The distance between the cars is decreasing at 2 o'clock. Distance is decreasing at 2 o'clock. What is happening at 4 o'clock, though, notice, it's positive. dl dt is positive 8.36 miles per hour. What's that mean about L? That means L is getting larger. The cars are getting further apart from one another. Right? Distance is increasing between the cars. So it's kind of interesting. Initially, the cars are getting closer together, but then at some point in time, really between 2 and 4 o'clock, there will be a change, and then the cars will be doing what? Getting further apart from one another. And this is an interesting problem, which we're not going to solve here, but at what time would the cars be closest together? So if you think about they're getting closer and closer together, somewhere between 2 and 4 it changes and they start getting further apart. So at some point in between 2 and 4 o'clock they are the closest distance to one another. Okay. All right, so we're going to stop here, and we will look at 2 more examples in the next video.